All right. So before we kind of get going, I'll show you on Canvas. So what I've done, so these are kind of anything on Canvas that doesn't kind of count towards your grade in terms of being used. So like the first and second exam, here's kind of where you took it. Thank you. Wait just a second, we're catching up in class here with the screen. There you go. So these are the ones that were kind of showing out of 104 points. Here's kind of current assignments, that additional practice kind of set of questions. And then what I added in down here, so you've got kind of all your quizzes count for 10% of your overall grade. The Excel assignments count as 10, Connect 10, Learn Smart 10. And then I have kind of identified everyone's lowest and highest exam score using these two what look like new assignments, but they're really just taking your kind of looking at exam 1, exam 2, whichever your highest exam was, it puts it in here. Whatever your lowest exam is, it puts it in here. It's counting your highest exam as 30%, your lowest is 20. So the kind of remaining 10% of the grade comes from the final. Now, obviously, if you do better on the final than you did on these first two exams, the final becomes your highest and is weighted 30, and those things get shifted around. But this is kind of why I added those in, because for some people, their lowest exam was exam 1 and not exam 2. So these capture that. Okay. Other than that, we've got that Connect I put up there. It was due 2 weeks from last Friday. After we're done with class today, I'll put up the next Excel assignment. It'll look very similar to what we did last week in Excel, as well as what we end up doing today. Okay. Any questions for me before we kind of get started here? Okay. All right. So we left off looking at confidence intervals for the difference in sample proportions. Okay. So here's our lower and our upper bound equation. We said our standard deviation for the difference in sample proportions looks a little bit different, right, than it did for sample mean. So this was our standard deviation for the difference in sample proportions. It took the variance of the distribution for the first group's sample portion, and then the variance of the second group's sample portion. Add them together, then we take the square root of the standard deviation. So we can calculate this intermediate step a lot of the time, and it makes it a lot easier for us. But we can also plug it in all at one time. Okay. So the example that we were looking at, it was like 84% of people in 2011, 82% in 2010 were in favor of healthcare coverage for everyone, and they had slightly different sample sizes, and we could build the confidence interval for what that true difference was. I think we worked through this last class, and we ended up finding it was negative 0.03 to 0.07. So this confidence interval included some negative values, some positive values, and then it also included 0. Right? So if it includes 0, then one of the true differences could be 0, that they're exactly the same. Right? So based off this confidence interval, we can't say a whole lot about what the true difference is in these population proportions. So we're just going to work through a very similar example again today, kind of starting out. So let's say I have that same survey, but I've got the percent of people who have unfavorable views of the Affordable Care Act, right? So we've got 0.51 in 2011, 0.48 in 2010, 600 and 607 are our sample sizes. Those are the only things that we needed for these confidence interval equations. We plug all those values in. The only thing left we need is what z-score gives us alpha over 2 on each side of our confidence interval. So if we look at our problem, our alpha, we had a 99% confidence interval. So why did I think that was on the dot cam? No, come on. Oh, wait, I do want you to see that. Oh, no. Okay. So 2011, sample proportion was 0.51. Sample proportion in 2010, 0.48. We have our sample size in both years. This one was 607, this one was 600. At the 99% level, our alpha should be, well, what's the amount outside the interval in decimal form? 0.01 here. Right? The 99% confidence interval, 1% is outside, and decimal form is 0.01. So kind of what we're thinking about is from that standard normal distribution, what z value gives me alpha over 2 on each side of my confidence interval. Right? Well, if my alpha is 0.01, 0.01 divided by 2 is 0.005. So the area that I want in each tail is 0.005. I'll go to my standard normal table, go around, I hunt for 0.005. Oops. It's going to be down here. So it looks like it's in between these two. So negative 2.57, negative 2.58. Well, remember our confidence interval already incorporates the positive negative sign, right, to our upper and our lower bound. So we'll think about 2.58 kind of being that z value we want, right? Going 2.58 standard deviations below to get the lower bound, going 2.58 standard deviations above to get our upper bound, okay? So now we really should have everything that we need. So I actually headed out to the third decimal here, and I'll show you how I got that in a second. So now I have everything I need to kind of plug these in and calculate my confidence interval. Okay? So I get negative 0.04 to 0.1. Right? It's kind of hard to see it. The negative sign trailed off there. I mean, at this step, once you have that z value, it's really just a matter of plugging our values in and being able to use our calculator. Now, what could have made it a little easier, calculate this ahead of time, and then you would just have one value to plug in here. So when we do the Excel example later, I'll kind of show you what that looks like a little bit more detailed. So we've got negative 0.04 to about 0.01. So if I'm thinking about the true difference in those proportions, so kind of this is my true difference, true population difference, it's anywhere in this range, right? So let's say it's a positive value. That would mean that the proportion in 2011 was higher, or more people had an unfavorable view of it, I think is the way the question was. I could have found the difference was negative, which would have meant the proportion in 2010 was actually higher. Or it could have been that difference was in fact 0, because 0 is one of the ranges or one of the values in this range, which would mean that if the difference is 0, that they were exactly the same across the 2 years. That could be one of the true differences. Right? So this confidence interval, we can't really say anything with a lot of certainty, right? Because it could be negative, the difference could be positive, or the difference could be 0. All right. Any questions over any of that before we keep moving? Okay. So if we can do confidence intervals, we can also do hypothesis testing. Okay. So, whoops. If we had this kind of set up for problem 1 where we're sampling from 2 populations, so we'll have 2 sample sizes, 2 sample proportions. We also know that the variance on each sample proportion will be equal to kind of this equation here. So one thing that ends up being true is if we want to calculate a test statistic, that's going to be a little bit different than with confidence intervals. So because we have different sample sizes across these variances, when we add these two or not really adding them, I guess we're subtracting these 2 sample proportions from each other, right? Taking one group minus the second group. That in order to make sure that our test statistic comes from a standard normal distribution, that the variance of the difference in sample proportions is going to look a little bit different. Okay? So this is going to look a little bit different. And essentially, it's weighting these distributions because the variance of each statistic depends on a different sample size. So when I add them together, I need to make sure that one of these variances is kind of getting weighted more than the other. And so when I start using this weighting, I kind of, we work through the mathematical proof, but what ends up being true is the standard deviation of the sample proportions when I weight these variances ends up looking something like this. So we calculate this P bar ahead of time. This kind of factors in this weighting, how much each one of these proportions is going to influence the standard deviation of the difference in those proportions. Once I find P bar, I plug that in, plug in my sample sizes, my sample proportions. The only thing left I have is this assumed true difference, which for all the examples we're working through, that assumed true difference is 0. So this almost like drops out. So this becomes pretty easy, okay? So that's going to be the only step that's different. All the steps are exactly the same as when we're looking for the difference in sample means. We still use the standard normal distribution. We look up critical values the same way. We look up p-values the same way. Nothing changes there, okay? The only thing that changes is that test statistical equation. So let's say we were looking at maybe some election data from the last election, and prior to it, we found that from a phone poll of 1,500 people, 49% planned to vote for Biden, 47% voted planned to vote for Trump. You want to test the proposition that Biden is going to receive more votes than Trump in the upcoming election. Okay? So if we think about, we want to test for, that's our alternative hypothesis. And what this is saying is that the proportion of votes for Biden are going to be greater than the proportion of votes for Trump. So if we're thinking about, okay, well, that's great, but when I write my alternative hypothesis, I need to have this difference. So if I subtract like the probability of Trump from both sides here, what I'd end up with on the left is that true difference. What I end up with on the right is that it's greater than 0. So if I want to test for whether or not Biden has a greater proportion than Trump, what I'm really saying is the difference between the two something that's positive. So I assume the opposite is true to stack the deck against myself, which is that difference is less than or equal to 0, which if this difference is less than or equal to 0, that would mean that Trump has a higher proportion, right? So I've assumed the opposite is true. So here's my null alternative hypothesis. So I look at my alternative hypothesis, similar to when we were doing one population examples. I've got a greater than sign, so I'm thinking about I have a right-tailed test. Okay? So if I have a right-tailed test, what's going to be true about my critical values? I'm trying to find the critical value that gives me alpha in this upper right tail, and alpha is like 0.01, 0.005, and 0.1. Well, that standard normal distribution is centered around 0. So if I want an area smaller than 0.5 in the right, my critical values are going to be positive. Okay? So here I've only got positive. Okay, I can't rule anything out, but I want to find the critical value at the 1% level, so alpha being 0.01. So we can look things up in my standard normal table, or, all right, so if I look it up in my standard normal table, I want 0.01. Well, if I look up 0.01, that's actually, the table always reads as the area to the left. So it would give me my critical value, but negative, right? So I could look up here, 0.0, why are my eyes not working? Right in between here. So negative 2.32 and negative 2.33. So, okay, negative 2.33, but I have a right-tailed test, so positive, right? Or I could have said, okay, instead of looking up alpha and remembering, oh yeah, it's a right-tailed test, I know that if there's 0.01 to the right of this critical value I want, that there would be 0.99 to the left. So I could come down here, look up 0.99, looks like I'm in between these two values. So 2.32 and 2.33, we take the higher of the two, we would have found the exact same thing. We could even go a step further, and we can use the student t-table to cheat a little bit. Remember we said that the last row of this student t-table represents my standard normal values, just out to the third decimal. So if I want the area of 0.01 in that upper right tail, the z-value that would give that to me, 2.326, which was, yeah, we were in between 2.33 and 2.32 before. So this is a little bit more precise, right? So multiple ways of doing the same thing here, but we get this critical value of 2.326. So if I'm thinking about here, 2.33 to the second decimal. So like, here's my rejection region, okay? Any questions on that before we keep moving? Okay, so the next step, all right, is if I have my critical value in rejection region, what's my test statistic? Well, if I'm looking at this, first of all, 42 is a ridiculous test statistic, right? I mean, this means I found the sample difference I found was 42 standard deviations away from the assumed true difference of 0. So I'm doubting that B is going to be the correct answer. But really at this point, I don't, I can kind of show you, but, writing it out I don't think helps a whole lot. It's really just we go back and we say, look, I know I've got this, where was it? I know I've got this test statistic equation. It's just a matter of plugging everything in. When I have that assumed true difference of 0, it makes it a lot easier, right? So we go down here, identify the piece of information I was given. I've got my critical value. The next step is finding the test statistic. So it's just going to be using this equation and write the intermediate value of p bar. So I plug everything in. My sample sizes of 1,500, sample portion of 0.49, 0.47, and I get, here it's 0.48. So this is a unique example where both groups have the same sample size. So really, like, p bar is just going to be kind of the average between the two proportions if all you're looking at are sample sizes. Or sorry, if all you're looking at is something with the same sample sizes. Now, as those sample sizes vary, then the kind of this, is going to weight the group that has a higher sample size more. But essentially, that's what p bar is doing, or capturing. But here we just plug it in. We now have the intermediate value we need. Plug in 0.48, plug in our sample size of 1,500, plug in our sample proportions, the assumed true difference of 0, and we get our test statistic here, okay? So 1.097, if I were to plot that, 1.097 falls somewhere over here, okay? So it's not in our rejection region, so we say we would fail to reject, right? We did see sample evidence that supported the alternative, right? That we found a positive difference here. However, it wasn't strong enough given the sample sizes to say that the true difference is in fact not less than or equal to 0. All right, we can't reject that null hypothesis. Any questions on that? Okay. Now, I could have also used the p-value approach here. Remember, for a right-tailed test, the p-value would be kind of this area to the right. Okay. Well, I can visually already see my p-value is going to be greater than alpha here, right? But what exactly would it be? Well, 1.097, I have to go to my standard normal table, so I'm going to round it to the second decimal, so 1.10. 1.10, the area to the left, right, would be 0.84, I lost it. Oh, sorry, 0.8643. So kind of the area to the left here, 0.8643. I wanted the area to the right, so 1 minus that, or approximately 0.14. Okay. So if I'm thinking about now, okay, which of these levels can I reject at? Well, my p-value was approximately 0.14. So if I'm thinking for different alphas, so 0.1, 0.05, and 0.01, is my p-value less than alpha here? No, no, no. So I fail to reject at all levels, which, if we would have found critical values for the different levels as well, we would have ended up seeing was the exact same rejection decision that we were making there. Okay. Questions on that before we keep moving here? Okay. So let's do one that's a little bit harder, a little bit trickier. So let's say we had a survey and we wanted to look at the true difference in sample proportions for 2010, 2011. And we've got our sample sizes, we've got our sample proportions of 0.84 and 0.82. And we want to test for whether or not people have different views. So now we're looking at whether or not they ensure, favor ensuring healthcare coverage for everyone. Well, what we're testing for here is what we're really thinking about is, if they're different from each other, we're saying, is that true population proportion in 2010 and 2011, is that Are they not equal to each other, right? Are they different from each other? Which is really just saying, is that difference not equal to 0, right? If I rearrange this and I subtract the probability from both sides, I'd have what? 2011 minus 2010 proportion, not equal to 0. This represents our difference, right? Are the views different from each other? Are those proportions anything other than each other, which would mean the difference is going to be something other than 0. So that's my alternative hypothesis. So if I've got my alternative hypothesis is that that difference is not equal to 0, I assume the opposite is true, which is that it in fact is equal to 0. Okay. So here I've got a not equal to sign. So evidence on either side could go against the null. So I've got a two-tailed test, right? Not equal to sign, two-tailed test. Well, from here, if I've got a two-tailed test, what's going to be true about my critical values? Well, I'm looking at that standard normal distribution. For a two-tailed test, we're saying what critical values give me alpha total in the tail. The tails. So if alpha total is in the tails, that would mean there's alpha over 2 in each tail. So notice if I want, I believe this is the 99% level. Oh, sorry, I didn't know. Yeah, the 1% significance level or 99% confidence level. We're going to have pairs of critical values. 99% confidence level or the 1% significance level, alpha is 0.01. So alpha over 2 is 0.005. Well, we already did this earlier at the confidence interval example, right? So earlier when we wanted the 99% confidence level, alpha was 0.01. We were really just looking for the z-score that gave us alpha over 2 in each tail. Well, the critical value is a z-score. So when I want to find alpha total in the tails for a two-tailed test, alpha over 2 in each tail, it's the same process as when we're looking up that value for the confidence interval. Okay? So when we looked that up before, we looked up 0.005, we found 2.58, and we would have kind of negative 2.58 here. So here's our critical values. We can kind of think about, there's our rejection region. Okay. Any questions on that before we keep moving? Okay, so we've got our critical values. What was it, so I've got it out to the third decimal here. Once again, how did I do that? I cheated. I used that last row of the student t distribution to look up 0.005. So the next thing I need is my test statistic. Right? Now, I found a sample difference that's positive. So that should tell me I'm a certain number of standard deviations above the assumed true difference, because the assumed true difference is 0. So I should have a positive test statistic. But really at this point, it's just a matter of plugging the values in. Right? So we identify the two sample proportions, the two sample sizes. We've got our critical values for the two-tailed test. We have to use these equations to find the test statistic. So we first calculate p bar, right? Plug everything in here. We then plug p bar into our test statistic equation, sample proportions, sample sizes, assume true difference of 0. We end up with this test statistic of 0.925. So, at this point, it's really just a matter of identifying, I'm looking for the difference in sample proportions. So this is my test statistic equation that I need to use. At that point, it's just a matter of getting the values plugged in correctly. So we've got this test statistic of 0.92. And we can kind of see that's not going to be anywhere near our rejection region. Okay? So we're definitely going to fail to reject here. We can't say that views have changed at all. Any questions on that one? Okay, so we failed to reject there. Yeah, I think I'll end it kind of there. If there's no more questions before we jump into kind of some Excel stuff. So I'll wait just a little bit. So anybody has any last questions? Okay. So let's go back to this hypothesis testing blank file. I kind of saved the work we had done last class. which is we had done some stuff with the difference in sample means. Okay. So this time, and I can't remember, it looks like I got rid of the confidence interval stuff, but I'm also going to delete all of this stuff as well down here, p-value and the critical values down here. So just like last class, I was working off two data sets. So the first one was Midwest schools. And instead of using total undergraduates, I'm going to use this variable that just is a 1 if they have more female than male students, and a 0 if they have more male than female students, right? So this is a 1 if they have more female students, 0 if not. Well, I then have a 1, 0 variable. I can find the sample proportion of that, the proportion of schools that have more female students in the Midwest, simply by taking the mean of that 1, 0 variable. I then can find the sample size using that count function. This should be nothing new. Hopefully we're getting kind of used to and comfortable with this. We've used this a lot before. And then similar to last class, I kind of just put this all on the same sheet. So here I've got the South data set. So I have the same variable, which is a 1 if they have more female students. So I found that proportion by using the mean function. And now I've kind of referenced the values that I found in the other sheet so that I have everything together. So I've got 2 sample proportions, 2 sample sizes. What I'm going to be interested in is the confidence interval for the difference between the Midwest and the South for having more female students. Right? So if I go back, what's the equation I'm going to need to use? I'm basically going to use Excel to be a calculator because I already have now my sample proportions and my sample sizes in Excel. The only other thing I need to do in Excel is find that z-value, the number of standard deviations away I need to go. Right? So similar to when we were doing this for sample means, I said we're going to use the norm.s.inv. Right? We know the area we want on each side of the confidence interval. We want to know the z-value that gives that to us. So we're going to go alpha over 2. Right? Now the issue with this is it always looks at the left side of the distribution, so it's going to give us a negative value. We already have the positive and negative signs built into our upper and lower bound equation, so we just want to take the absolute value here. That should give us the z-score. Now, when I copy this down, notice these are the exact same 3 values that I was using when I was looking at the difference in sample means from last class. Okay? And it should be. It's the same alpha over 2 on each side of the confidence interval. I should be using the same z-values. From there, it's a matter of getting our equation entered into Excel. Now, what I'm going to do is I'm going to break it down into 2 parts just to make it a little easier. I'm going to kind of calculate this, which represents the standard deviation for the difference in proportions. I'm going to do that in a different cell. So I'm going to do that up here. So standard deviation of difference in sample proportions. Okay? So I'm going to do that up here. And that was simply the square root of each population proportion times 1 minus that proportion divided by the sample size. Okay. And then add to that the second group's sample proportion times 1 minus that group's sample proportion divided by their sample size. Okay. So I just calculated that intermediate step up here in this other cell. Right. Now when I'm finding my lower bound, well, that's just take the Midwest sample proportion minus the South. Now I could then here I'll subtract my z-value, right? Subtracting my margin of error, which is my z-value times that standard deviation in sample proportions, or the number of standard deviations I want to go to the left times whatever the standard deviation on the statistic I'm interested in is. And the statistic I'm interested in is this difference in the proportions. Okay? Any questions on anything up to this point? Do you want to see a cell again, or? Okay. So if I want to use this and kind of copy this down to do my next 2 levels of confidence, everything's going to stay the same. The only thing that changes is the number of standard deviations out I'm going, right? So the only thing I want to change is that z-value. So I'm going to select everything else. Here it is. Hit F4 or Command T on a Mac and put $ around everything that's not the z-value. I'm then going to copy this down. Now I've got the lower bound for each level of confidence. Now the upper bound is going to be the exact same thing. So I'm going to go in, I'm going to copy, hit enter to get out of the cell, and I'm going to paste. So this should be the exact same thing, but for my upper bound, I add that margin of error. Now I copy that down. Oh, this is going to be a pain because these are images. And I've got my upper bounds. Now notice each one of these confidence intervals includes the value of 0. Right? So if it includes the value of 0, if I do a hypothesis test for that value, so I don't think I can't remember if I did this for the last section or you guys. So if I do, where is this? Here we go. So before, remember when I was doing confidence intervals, when I was doing this one for the kind of differences here in 2011, 2010, here were like the range of possible values. But when I do a two-tailed test, if I do a two-tailed test and I assume the difference is any value in this range, well, these are all potential different values, at the alpha of 0.01 at the 99% level, all these values are possible true values for the difference in these 2 years. So when I do a hypothesis test, if I assume it's 0, which was one of the values in that range, I should fail to reject, right? So sure enough, once I worked through all this, I had a test statistic that I definitely failed to reject. So the two-tailed test and confidence intervals line up. So where are we at in Excel there? So I've got these confidence, if I do a hypothesis test for 0 at a two-tailed test, I should be kind of failing to reject 0. However, what if I want to do a one-tailed test? Well, it doesn't necessarily always line up, right? And we work through this example, we'll see that, in fact, we don't fail to reject all the time for this assumed true difference of 0, even though when I look at the confidence intervals, it's in every single one. It's because this would be reflective of a two-tailed test, evidence on either side mattering. So we have this left-tailed test, right? I'm assuming that the difference is greater than or equal to 0. So I left these in here. All I did here was take that test statistic equation, right, which we have right here, and the intermediate step P bar, and I basically just entered these into Excel, right? I entered everything I have in Excel, everything I need, is in Excel. So it was really just a matter of getting those formulas entered into Excel correctly. So here's the P bar formula. Here's my test statistic. Okay. And here I even subtracted the assumed true difference of 0. I technically didn't have to do that. Subtracting 0 won't change anything. But once I have that test statistic, right, how do I find that p-value? Well, I'm doing this standard normal distribution. The test statistic I found was approximately negative 0.14. So the p-value would be the area to the left. Right? Remember, this was my test statistic. Okay. So I can, in Excel, use the norm.s.dist function, right? I now, norm. I now know the z-value, and I want Excel to tell me the area to the left. So the z-value I have is negative 1.48, comma 1 tells me the area to the left. For a left-tailed test in Excel, I'm done at this point. Right? This should give me the area to the left of my test statistic. So it's about 0.07. Okay? So if I look, at these 3 different levels of alpha, if I only reject if the p-value is less than alpha, can I reject at the 0.1 level or 10% level? Yeah, my p-value is less than that. Can I reject at the 0.05 or the 5% level? Well, no, my p-value is not less than that. So if it's not less than 0.05, it's not going to be less than 0.01. I'm going to reject, fail to reject, and fail to reject. Okay? And that's just from simply kind of looking at that and comparing that. Now, I'm going to show you another way of doing this. So here's the critical value approach. So the critical value approach is going to be, okay, what critical value gives me alpha in this lower left tail? Right? Well, if I look at an alpha of 0.1, right, in Excel, what I do is say, okay, I know the area in the tail, so norm, almost lost a marker there, norm.s.inv, I'm working in reverse, I'm working inverse, right? I know the area in the tail. I want Excel to tell me the z-score. So area in the tail is 0.1. Well, I'm done, right? I'm telling you the area in the tail because I have a left-tailed test. Copy this down. I get my 3 critical values. So I could plot these 3 critical values, see where my test statistic lies, but there's also a rule that we said will always work. And the whole thing was the reason why we reject when the test statistic is in the rejection region, it's the idea that the test statistic is larger in absolute value than the critical value. And the reason we have to take the absolute value here is because, if we look at the left side, we're dealing with negative values, right side, we're dealing with positive. So more extreme is positive for a right tail, but it's actually less than for left tail. But if we ignore the signs, this will always hold. So what I'm going to do here is use an if statement. If the absolute value of my test statistic is greater than the absolute value of my critical value, comma, if that's true, put the word reject, right? My test statistic is more extreme than my critical value, I reject, comma, if it's not, I'm going to fail to reject, okay? So, oops, I'm just making a little if statement there. Now, when I copy this down, I want to be able to test against different levels. Well, I'm going to be testing against different critical values, but I'm still using the same sample evidence, that same test statistic that I found. So I'm going to make sure that I freeze the cell reference where my test statistic is, because when I copy this down, I just want to do that rejection decision for different levels, for different critical values. So I copy this down, and sure enough, I get the same outcomes as the p-value when I was comparing the p-value to alpha. I rejected the 10% level, but not at the 5 and the 1% level, okay? Any questions on this? I'll keep moving here. Okay. Is there anything else I want to say here? I think we're good here. But yeah, you can kind of see the steps are like, you can do the critical value or p-value approach. The steps are very similar when we were looking at the difference in sample means last class, or the difference in sample proportions. The only thing that's going to change is our test statistic equation is a little bit different. And then in confidence intervals, when we're looking at the standard deviation of the difference in sample proportions, it looks a little different than the standard deviation for the difference in sample means. But we look up the z-values for confidence intervals the same way. We look up p-values the same way. We look up critical values the same way. The principles aren't a lot different. It's just slightly different equations that we're using. Okay. Any questions on anything we said here? I feel like I forgot to do something, and now I'm wondering what it was. I think we should be good. Yeah, I think we should be good. Okay. Well, that kind of wraps up the difference in sample proportions. I'm just going to briefly introduce the next idea, which we'll kind of tackle on Friday because we have a study day this Wednesday, so we won't be meeting for class. So we'll pick up this on Friday. But it's basically that what happens if we're looking at the difference in sample means and we don't know the population variances? All we have is the sample variances. So this is the more realistic scenario. Well, we're going to use the student t-distribution just like we did for one population examples. However, the difference isn't quite normally distributed. So you can kind of imagine, when I was drawing out like, okay, we know that each sample mean has its own normal distribution. So what's the most likely difference we see? And then we can plot out, okay, now the difference will be also normally distributed. But, right, if we have two different student t-distributions, like let's say my first sample is a sample size 50 and my second group has a sample size 30, will they be coming from different student t-distributions? Before, when we were looking at the difference in sample means, each sample mean distribution was normally distributed. Here, each sample mean will be distributed with a student t-distribution, but it could be a different student t-distribution. So when I'm looking at the difference between the two, I still construct my confidence interval in almost the exact same way. So, here we're thinking about what we were doing before compared to what we're doing now. So remember, I was looking for the difference in sample means when I knew the population variances. And this guy here represented the standard deviation for the difference in sample means. Okay? It's going to be the exact same thing. It's just that now, when we only have sample variances, this represents the kind of standard deviation for the difference in sample means just using the sample variance. And because we're using sample variances, we need to use that student t distribution, but we're still basing it kind of around that same sample difference. Right? This kind of this difference in sample means, another way of thinking about this is my sample difference I found. Now, that's great, but if I just said, well, what if sample size 1 and 2 aren't the same, then the distribution of my sample means are both coming from a different student t distribution. So which student t distribution do I use? How do I find my degrees of freedom? Well, it's not going to be simply n minus 1 anymore, right? What ends up being true is it's going to be some like weighted combination of the two. And so it uses the sample variance and sample size from each group. I'm not going to expect you to use this on an exam. And a lot of times, even on the Connect homework, I'll give you some, they'll try to give you an assumed true degrees of freedom. If you're having difficulties finding kind of the degrees of freedom, let me know on that Connect homework. But I won't ask you to do it in an Excel, and I won't ask you to do it on the exam. There's potential in some of those Connect assignments, they might ask you to calculate that degrees of freedom. But I don't want to use it on the exam or something where time is limited, because this is really just a matter of like getting this entered in correctly. And it's kind of hard, right? It's a messy equation. So how many degrees of freedom, right? All of them. So I'll be giving you this assumed true degrees of freedom as we work through these examples. It'll make it a little bit easier. But in practice, you'd actually, have to calculate it. Okay. So the steps are going to be exactly the same as what we were doing before. It's just we use a student t distribution, and which student t distribution do we use? Using that degrees of freedom, we're going to have to use this equation, or I'm going to have to tell you what this equation would give us. Right? But other than that, it's the exact same procedures. Right? So we'll pick up on this on Friday, but I'll show you on the Excel assignment that I'll post after class today, what we've done on this South worksheet, and I'll post the one, like I'll call it 2 population HT in class work. So the completed one is up there, but I did a couple things a little bit differently and added some stuff as we're working through it in class. So I'll upload what we've done in class here as well. Oh, I know what I want to mention. So your next class, we're going to start doing things with this mail data worksheet. So you can get started on the Excel. You can probably work through the first kind of half to 2/3 of it, just based off what we've done on this South worksheet. Okay. If we go to this mail data sheet, what we're going to do on Friday, right, because we have a study day Wednesday, is look at the difference in sample means, but only having a sample variance. So we have to use a student t distribution and this new degrees of freedom equation. So on that Excel assignment, once you get to that point, you're not going to have to enter this equation into Excel. I will have the assignment set up so that I have something like this already typed in, right? What that degrees of freedom would be, kind of based off of the sample variance, sample size you found. Okay. So notice here, I've got that equation entered in. Took a little bit of time to make sure I had the right parentheses and everything, but that's what it would look like. And then we always round it down or kind of floor it. In Excel, floor would take like 89.9 and push it down to 89. So we're always kind of erring on the side of caution, giving ourselves a little bit lower degrees of freedom. Okay. So that would already kind of be in the Excel assignment when you upload it, like originally, like before you even do any work. So that'll be kind of a nice thing that will kind of make this a little bit easier for us. All right, any other questions for me before we kind of get out of here for today? No? All right, so we'll pick up back up on Friday. We'll finish up these 2 population examples. We should then just have matched pairs and then the linear regression stuff kind of from there on out. If you have any questions about kind of your grade or grading of the second exam, please feel free to reach out. I should be, my GAs are helping me with those 3rd Excel assignments. Those should start, you may have already seen some of them graded, or they should start kind of showing up as graded here soon, which will then give you a perfect idea of where you're currently at in the class grade-wise, okay? All right, we'll see you on Friday.